Alright, gang, here we go. This is for Chem 1, Unit 12, Part 6. We're talking about the autoionization of water. Should be fun. Alright, so we kind of briefed over this a couple of videos ago. We talked about how water is amphoteric. Remember, amphoteric means that it can act as an acid or a base. So let's look at these two reactions here. We've got sulfuric acid reacting with water, okay, and it's going to form this bisulfite anion here, the conjugate base of this guy, and then water, right? Oh, this should be H3O plus. Okay, so anyway, so you got sulfuric acid reacting with water, and so the water here is gaining a hydrogen as it goes from here to here, and so because of that, we know it's acting like a base. So in this case, water is acting like a base. However, if we stick it in with ammonia, the water is going to, when it goes from here to here, it adds, or it loses a hydrogen, so it becomes a proton donor. So therefore here the water is acting like an acid. So what that really amounts to is water is amphoteric. It can act like an acid or a base. So when we put water in with itself, what occurs is every so often two water molecules can hit each other just right so that they can act like an acid or a base with itself. Okay, so if you have these two water molecules, these two guys here, and we could just as easily write this out as H2O plus H2O. Okay, if we take these two guys and they hit each other just right, one of them will act like an acid and donate its proton, and the other one will act like a base and gain a proton, and you'll actually form your hydronium and your hydroxide within water. Okay, now this is forming ions, and because it's forming ions, we know that it should be an electrolyte and should therefore conduct electricity, and it actually does. So water, I've kind of lied to you a little bit. I've told you water, pure water, doesn't conduct electricity. It actually does, but it's just really bad at it. Okay, so a pure water has electrolytes in it just all by itself. And based on conductivity studies, we found that at 25 degrees Celsius, the concentration of your hydronium is equal to your concentration of hydroxide. And that makes sense because for every one hydronium you make one hydroxide, and those are equal to 1 times 10 to the minus 7th. All right, and so this is an important relationship. Therefore, we know that we can take these two values here, all right, and using this idea called KEQ, and we'll talk about what this means when we get to equilibrium. It'll be a couple of units, but for now, just take my word for it. We've got this value called KEQ, and we can take these two concentrations, set them equal to each other, and it's equal to this 1 times 10 to the minus 14th, and this is known as your KW. Okay, so really what this amounts to is at any value, okay, of our concentration of hydronium and hydroxide, what we get is this guy here, a hydronium. Concentration of the hydronium times the concentration of the hydroxide is always going to be equal to your KW, and this is true at any 25 degrees Celsius. So it doesn't matter what you started with, pure water or something mixed with some acid or base, your hydronium and your hydroxide multiplied together will always equal your KW, and your KW is always equal to this 1 times 10 to the minus 14th. All right, so this is your big takeaway. What do you need to take away from this? Number one, your hydronium times your hydroxide equals your KW, which is equal to your 1 times 10 to the minus 14th. So therefore, as your hydronium increases, the hydroxide must decrease. They always go hand in hand. If your hydronium goes up, your hydroxide goes down. Because if they both go up, then your KW would be higher than 1 times 10 to the minus 14th, and it's not possible, okay? And so we can use this equation from number one to solve for any concentration of hydronium or hydroxide. We just need to know the other one. Okay, so what does this amount to us? Well, we can determine based on the hydronium concentration or the relationship between the two of them, we can figure out if we have a neutral solution, an acidic solution, or a basic solution. Neutral solutions are when both of your two ions that you need, your hydronium and your hydroxide, are equal to each other. So they're both equal to 1 times 10 to the minus 7. They both have to be equal to that. In an acidic solution, your hydronium concentration is a greater than 1 times 10 to the minus 7th, so therefore your hydroxide solution has to be less than that. Okay, so in an acidic solution, you have more hydronium than hydroxide, and then basic solutions are the opposite. You have more hydroxide than hydroniums, and your hydroxide ion concentration is greater than 1 times 10 to the minus 7th. All right, so let's do some practice problems. It says, what is the hydronium ion concentration of 1 times 10 to the minus 2nd molar NaOH? All right, so NaOH is going to turn into this guy here. All right, and so it's going to form, sodium and our hydroxide. So that means, and this is a one-to-one relationship. So we know that for this is a strong base. It's one of our 7 strong. So every 1 sodium hydroxide is going to break up into 1 hydroxide. So that means the concentration of our hydroxide is going to be equal to our 1 times 10 to the minus second. All right, NaOH. All right, so what does that mean to us? Well, now they want us to find the hydronium ion. Remember, hydronium ion concentration, that would be our H3O plus. And we just established that the hydroxide times our hydronium is going to be equal to our Kw. So that means our hydronium ion concentration, our H3O plus, is going to be equal to our Kw divided by the concentration of the hydroxide. All right, so the Kw is 1 times 10 to the minus 14th. All right, and then hydronium or hydroxide concentration is 1 times 10 to the minus second. All right, so we get 1 e to the minus 14th divided by 1 e to the minus second, and we get 1 times 10 to the minus 12th. 10 to the minus 12th. So that is the concentration of your hydronium. And then it asks us, well, what is this, neutral, acidic, or basic? Well, remember, with neutral, they're equal to each other. These are obviously not equal to each other. And in acidic, hydronium needs to be greater than hydroxide, and then basic, hydroxide needs to be greater than hydronium. In this case, this is our hydronium, and then our hydroxide was equal to this guy here. Okay. Oh, I don't know why I wrote that. But anyway, so this guy is obviously bigger than this one because it's only times 10 to the minus second. So therefore, this solution is basic. So basic. All right. All right, let's try this guy. It says, determine the hydronium and the hydroxide concentration in a 9 molar H plus solution. Well, this is easy. H plus and hydronium are the exact same thing. So if it's 9 molar H plus, this is the same thing as H3O plus. All right. I don't know if you can hear my son, but he's throwing a temper tantrum up there. All right. So anyway, so we get H3O plus. So the concentration of hydronium is the same as the other one. It's just 9.0 molar. Okay. And then to find the concentration of hydroxide, OH minus. All right. That's going to be the Kw divided by our H3O plus. Super easy. All right. So that's our 1 times 10 to the minus 14th divided by our 9. Okay, 0.0. So we get 1 e to the minus 14th divided by 9. Okay, and so we get 1.126 figs times 10 to the minus 15th, and that's molar hydroxide solution. All right, so there's the concentration of hydroxide. There's the concentration of hydronium. All right, and then is this acidic or basic? Well, the hydronium is obviously way bigger than the hydroxide, so therefore this solution is acidic. All right, so that's it. Not too bad stuff, just that one formula, learning about your autoionization of water, so on and so forth. Let me know if you do your practice problems. Let me know if you have any questions, and I'll see you on the flip side.